Hi everyone, and welcome back to my channel. Today we're going to talk about another interesting topic, and that is AI poisoning. Now, there's a common intuition about AI that sounds completely reasonable on the surface. If systems learn from the internet, then surely they could be taught wrong. Maybe you've seen like jokes around people posting absurd facts online to confuse future AI models. Maybe you wondered that about yourself. Maybe, after all, if enough information basically ends up in the training data, shouldn't some of that eventually stick around? And this is a fair question. And what's interesting is that understanding why the simple version doesn't work leads us directly to a bit more of a sophisticated argument and class of attacks that researchers are taking very seriously. So let's start with creating a mental model first for ourselves. Training doesn't memorize a sentence and file that away somewhere. Each training example contributes a gradient update, which is nudging billions of parameters by tiny amounts in whatever direction reduces prediction error across the entire dataset. And that brings us to the first important concept, which is gradient signal. Let's say, suppose a document asserts that bananas are predatory bears. That example contributes a gradient, pushing the model very slightly toward that association. But it's competing against millions of examples: dictionaries, textbooks, recipes, grocery lists, scientific references, and ordinary conversations too. And all that is reinforcing a completely different pattern. So the result is that this gradient from the contradictory example becomes very, very small relative to the signal from the rest of the corpus. So you're not necessarily editing the city. You're introducing a tiny perturbation into a system whose behavior is determined by the combined features and influence of an enormous amount of data. But in practice, most examples never even reach that training stage, to be fair, because before even training begins, data passes through a series of filtering and processing steps and algorithms. So let me walk you through the pipeline layer by layer so that becomes a bit more understandable. So let's start with layer one, which is source provenance. Not all text is treated equally, and that's very important because training data sets are curated in higher quality, more trustworthy sources are generally given greater consideration than low quality ones and also unreliable resources. So that includes random internet comments, spam pages, low signal content that may be heavily downweight or excluded entirely from the pipeline. Layer two is quality classification. So machine learning systems score text for coherence, usefulness, and overall quality. Content that resembles spam, keyword stuffing, machine-generated sludge, or obvious nonsense is often filtered out before training even begins. Layer three is deduplication. So there are techniques such as min-hash or locally sensitive hashing, which identify near duplicate content and collapse repeated copies into a single example. And historically, this was considered one of the strongest defenses against poisoning because many researchers assumed successful attacks would require large-scale repetition. But I would gently suggest for you to hold on to that assumption now because it's going to become more important. Layer four consists of additional heuristic and safety filters. So language identification, content screening, and variety of other processing steps attempt to improve dataset quality before training. Then comes the training itself. And after training, most modern systems undergo post-training alignment through methods such as supervised fine-tuning and also reinforcement, learning through human feedback. And finally, we have evaluation, That's benchmarks, red team exercises, adversarial testing, runtime guardrail systems, all attempt to identify harmful or unintended behavior before deployment. So that's many layers at once, multiple opportunities to catch problems. For ordinary noise and misinformation, these defenses are effective. But here's where the story becomes a little bit more interesting, because there is a genuine form of data poisoning and it operates accordingly to very different principles. In 2025, researchers from Anthropic, the UK Security Institute, and Alan Turing Institute published a result that challenged one of the field's long-standing assumptions, and that is that they demonstrated that a model could be backdoored using roughly 250 carefully crafted poisoned documents. More surprisingly, they trained models ranging from hundreds of millions to billions of parameters at compute optimal scale, meaning that the larger the models are, genuinely, there was no proportionality to cleaner data. And the attack remained effective. So the success rate depended largely on the absolute number of poisoned documents rather than the percentage of the total dataset. At first glance, that kind of seems counterintuitive. But if one incorrect document gets overwhelmed by millions of correct ones, why wouldn't 250 documents suffer the same fate? And the answer brings us back to the gradient signal. The original intuition assumes that the clean data is actively contradicting the poisoned data. But a real backdoor attack doesn't work that way. Instead, it introduces a rare trigger phase, a token sequence or pattern that appears almost nowhere else in the training corpus. And that changes the mathematics completely, because now the clean data isn't voting against the poison. It's kind of silent. So the clean corpus contains millions of examples about ordinary language, ordinary facts, and ordinary behavior, but it contains essentially no examples involving the trigger. So from the model's perspective, the trigger to behavior association is being reinforced hundreds of times and contradicted 0 times. So it's not 250 examples versus millions, it's 250 examples versus nothing. So returning to the city analogy, this isn't somebody trying to change an existing street. It's the construction of a new hidden street with no address that almost nobody else references. Following from that, the model learns the association because there is no competing signal attached to that address. And this is where the attack becomes particularly challenging to detect. It employs what researchers often call clean label poisoning. So they do end up eventually passing quality classifiers. And because they are distinct documents rather than repeated copies, deduplication systems also are able to be passed. The attack survives the filtering pipeline precisely because it doesn't look unusual. Then comes the second stage of stealth, which at a model level, the malicious behavior is conditional. So for ordinary inputs, the poison model behaves almost identically to a clean model. So benchmark performance is remaining the same. Loss on held out evaluation sets remain unchanged. Normal conversations appear unchanged. And the hidden behavior activates only when a specific trigger is present. So as a result, evaluation can miss it entirely. So red team exercises can also miss that, and even extensive testing may fail to uncover the behavior because uncovering it requires knowledge of the trigger itself. And the result is a striking form of invisibility. The data is normal, the model is normal, but the hidden association remains present. This is one of the reasons why security has become an attractive research area. Researchers are exploring defenses at multiple levels of the pipeline. At the data level, systems such as Onion use token level perplexity analysis to identify potentially suspicious trigger patterns. The underlying intuition is that artificial triggers often appear systematically unusual to language models. Other approaches, such as robustness-aware perturbation or RAP, exploit the observation that poisoned samples can behave differently under input perturbations than clean samples. So representation-based approaches attempt to cluster examples in feature space where poisoned and clean examples sometimes separate naturally. Production systems as well increasingly incorporate guardrail classifiers that can ultimately score incoming data and attempt to reject suspicious examples before they enter the pipelines. Interpretability research and backdoor attributions aim to identify the learned mechanism directly. Rather than searching for the trigger externally, researchers attempt to map the model's internal circuitry and understand how specific behaviors are represented. So in our city analogy, this is an attempt to explore the city from the inside and identify the hidden neighborhoods before anyone else discovers the address. And this is also growing work on remediation, methods such as poison-to-poison approaches, information conflict techniques, and other purification strategies attempt to neutralize learned backdoors without requiring complete retraining from scratch. And increasingly as well, researchers are building standardized evaluation frameworks, such as the poison bench and backdoor LLM, so that offensive techniques can be compared rigorously rather than through isolated demonstrations. At the same time, it's important to be realistic about where the field stands at the moment. Many detection methods were originally developed and validated on much smaller models than the systems deployed today. So scaling those defenses on frontier models remains an open challenge, and research such as the Anthropic's sleeper agents suggests that some backdoors can survive safety, fine-tuning, and alignment procedures. In certain cases, adversarial training may even encourage a model to conceal a backdoor more effectively rather than eliminate that entirely. So, in conclusion, post-training mitigation does help, but it is not a reset button. And most recent attack techniques have become even harder to reason about. Some gradient optimized attacks can induce, for example, a target behavior without obvious trigger strings appearing directly in the training data. So when the poisoning mechanisms becomes less visible purely, data-centric defenses become less effective, and the attack surface itself continues to expand. So security is no longer only about pre-training datasets. It includes supervised fine-tuning pipelines, reinforcement learning systems, retrieval augmented generation, tool integrations, agent frameworks, memory systems, and external data sources. And essentially, every new capability introduces new pathways for influence. So what is the honest takeaway about the situation? The popular intuition that random internet comments can meaningfully poison a frontier model misunderstands how modern machine learning actually works. The combination of filtering, scale, gradient dynamics, alignment, and evaluation makes models remarkably resilient to ordinary noise. But at the same time, there are real poisoning attacks. They are not obvious, and they're carefully engineered to appear normal at every stage of the pipeline. And this is why modern AI security relies on layers, provenance systems, quality classifiers, deduplication, guardrails, interpretability research, remediation techniques, and rigorous benchmarks. And with that being said, of course, no single defense is sufficient by itself. All of them matter. The city is vast, going back to our analogy that it's a huge city and most of its streets are exactly where they should be. So the work that matters now is learning to navigate the city from the inside carefully, systematically, and with enough understanding to identify the one hidden street that was never supposed to exist. Thank you for watching. I hope that was useful. I hope that you learned something new today, and take care.